All right, great. Again, please feel free to ask questions. Don't worry about the recording thing going on. That's not, oh my God, kind of thing. This is really just for us. So I'm not sure how I'm going to get it out on, so this may end up showing up on a YouTube for you guys. I don't know. We'll see. All righty. So let's start off at the very first thing, which is glycolysis. And so the very first molecule on the far left-hand side, what's that very first molecule? Very first one that goes right inside the cell membrane. Glucose, that's correct. Yes, it is glucose. All right, and what is the chemical formula for glucose?
C6H12O6.
There you go. So how many carbons do we have?
6.
So there's 6 carbons. Are there any phosphates? No. Do you see any in the chemical formula here? So there's 0 phosphates. All righty. So it first goes into the cell. So you see that membrane here, right? You see the membrane here? What kind of membrane protein does this one look like? No, the type. So it's not carrier. What's the other type? Channel. See, look at it. It's kind of like a channel. It's actually a gated channel, but yes, it's a channel. Don't worry about active or passive. That's beyond the scope of what you guys need to know. Okay? But you should be able to look and say, hey, yeah, that's a channel protein. Let's do that again, but with a different part of the flow chart. What about this right here? These two guys right here. What do those look like? Channel or carrier proteins?
Carrier. Channel?
They look like channel proteins.
Oh, you're just pointing to these.
Yeah, these two right here. These two. See the shape? So if it's got a hole that goes through it, it's going to be a channel protein. Could it still be active transport? Yeah, but we're not worried. This is honors bio. We're not worried about whether it's active or passive transport. Usually when you're shown a carrier protein that's in a membrane, it's going to look like all of these. You see all of these in the protein? These are all carrier. All right, are we good? All right, here we go. So, what is the first thing that happens to glucose? Gains of phosphate, good. So it goes from ATP to ADP, right? Okay, we need to check and make sure, and I'm sorry I'm being a little boring here, but we need to check and make sure that we have this stuff down. If I have ATP and it goes to ADP, what else has to come off? If this is a chemical formula, I went from ATP to ADP, so what else has to be over here?
Hydrogen?
Not hydrogen. I went from
Carbon?
ATP. What does ATP stand for?
Triphosphate and diphosphate.
That's diphosphate, so I can't lose or gain matter, so this has to be a phosphate. What if I had glucose plus ATP, which is what's going on here? I get ADP, and then I would also get, what would I get? What's the next molecule?
Glucose 6-phosphate.
And the 6 on there means that 6 is what carbon the phosphate is on, not how many. So that means if I had glucose plus ATP and I got ADP, I would also get
Carbon? Or no, yeah.
glucose, but what else would glucose have attached to it now?
Carbon.
Not carbon,
Phosphate.
phosphate. And I'm just going to do a little line and put a P on there so that you know it's attached. So my formula here would be C6H12O6, and then what would be on the end of it?
A P.
A P. Do you see what's going on? Okay. Phosphates carry energy. So here's my phosphates. There's my ribose. There's the adenine, the A part. So this is a chunk of energy. So I moved some energy from ATP to glucose. Did the energy in glucose go up, down, or stay the same?
Up.
Glucose energy went up. Everybody good so far? We okay? Do you remember what this is called when you add a phosphate to a molecule? We talked about it last semester. It starts with a pH. Does anybody remember? Asher, are we okay? Phosphorylation. If you don't know that, write it down. You can write it on here, but write it down. Phosphorylation. Phosphorylation. When you add a phosphate to any molecule, it's phosphorylation. Did glucose become phosphorylated?
Yes.
Yes. Did glucose gain energy? Yes. If a molecule is phosphorylated, does it gain energy?
Yes.
That's a concept you have to know. So on your study guide here for on your study guide for cellular respiration, series of enzymatic reactions that utilize electron carriers to synthesize ATP. We'll get to that. We're going to get to number 2 today. And then it's down here. Actually, it goes throughout the whole thing. Anytime you see where it says ATP that produces or gives or is used, that's the energy that's used to do this. We good so far?
Yes.
Okay. Everybody good? All right. So here we go. Here we go. Again, you do not have to worry about the names of all these different molecules. So how many times does glucose get phosphorylated? In other words, it gets phosphorylated twice. How many times do we use an ATP molecule? And that's 2, okay? So this molecule here, the molecule that's right at the split, this is fructose 1,6-phosphate. The 1 and the 6 just say where the phosphates are. How many carbons does the fructose have? Count on your sheet. Or you can even do it this way. Did we change any carbons? Did we lose carbon dioxide or add carbon dioxide?
No.
We didn't. So how many carbons should we have here?
6.
So we have 6 carbons. What about phosphates? How many phosphates do we have? 2. Where did they come from? ATP, right. So we have 2 phosphates. Did energy increase?
Yes.
Yeah, absolutely, energy increased. All right, here's your definition of what we are going to do for cellular respiration. So you want to write this down. Here is your definition for cellular respiration. It is to break down sugars to make ATP. That's the whole point. To break down sugar to make ATP. That's the whole point. To break down sugar to make ATP. To break down sugar to make ATP. Are we good? Okay, great. So, do you remember what glyco stands for? Sugar, and then lysis? To split. So the first part of our process is going to split the glucose. We add energy in because we want to get a bunch of energy out. So here's your next concept that sometimes kids struggle with. If I have these markers here, I got a couple of markers in my hand, and I have them sitting at this level, is there potential energy here?
Yes.
Yeah, because they're sitting up, right? Is there potential energy if I do this?
Yes.
The potential energy here is going to be different than if it was this way, right? We have potential energy in any molecule, so the amount of potential energy changes. In this case, it's going to increase. Why does it increase? Because the ATP added that energy in, and we're doing it to get it in such a way to where it's easy to split. Because it's really hard just to split the glucose right in half. Are we okay?
Yeah.
Okay, great. Alrighty, so the next thing that happens, we're not going to worry about any of the waters coming in and off. Again, this is honors bio. We don't really care about that. That's something that we cover more in AP or you'll get in a later college class. All right, so the next thing that happens when you look on your sheet here is we have this NAD going to NADH. Now, are you okay if I just write it this way? You have it like this on your sheet. Right? I would like to write it a little differently, and it just saves space for me, but it's the same thing. If you have a problem, I can go back to writing it the way it is exactly on your sheet. Let me make a little more gap here. So NAD goes to NADH, and it happens on both of these. Are we okay?
Yeah.
Everybody okay? All right. Does that molecule look familiar to you?
Yes.
What does it look like?
It looks like.
NADPH or something.
Perfect. Back rope. NADPH or pH2. What do you remember what that molecule did?
I know the like the top right of the photosynthesis chart.
And it went into Calvin cycle, right? What was its whole job?
So like storing energy.
Storing energy. This one stores energy. What do you think this one does? They're very similar.
Like generates it. Or,
Doesn't generate.
transfers.
It does. Both of them will actually transfer because they can carry energy. So this one will store energy as well. This one is used in cellular respiration. The bottom one is used in photosynthesis. Test question. Which of the following stores energy during cellular respiration? A, B, C, D. I could put both of these on here. You got to know cellular respiration, photosynthesis. Are we okay?
Yeah.
You okay? Alrighty. So if that's the case, we had some energy here, but we added to it. Now, did we add energy or did we take energy away from this molecule that was moving? Take energy away. So we took energy away, so now we're trying to get the energy out. What molecule do we want to have after we break glucose down completely?
Fructose. Or
What's the definition of cellular, what's the point of cellular respiration?
Break down sugar, it turns ATP.
To ATP. So what molecule do we want to have? ATP, right? Do we have it yet?
No.
No. You're going to find out later this molecule will actually get made into ATP. Alrighty, what happens next? Don't worry about the water. What happens next to these molecules as we go down this pathway? What happens next? Just based on what we've done so far. Like between number 4 and number 8, what happens?
ADP goes to ADP or ATP.
That's right. ADP goes to ATP. So what happened? Did we
lost a phosphate.
we lost a phosphate from here and we put it there, so did we take energy away from the molecules that we were breaking down?
Yeah.
We sure did. So we pulled more energy. Is ATP what we want?
Yes.
Okay, how many times did we do it on the top line before we got to pyruvic acid?
2.
Twice. How many times did we do it on the bottom line?
1.
Look on the bottom line that you have. You guys good on where we're at? So what about the line underneath? Because remember, it's split into 2 of the exact same molecules. So do we do the exact same thing?
Yeah.
So how many times does ATP get made down here?
2 times.
twice as well.
Oh, what's that? Okay, okay.
Remember, you do not need to memorize the names of these molecules. What I'm putting on the board is what you need to be able to do, what you need to be able to memorize, what you need to be able to recall. Okay? How many carbons does pyruvic acid have? Look on your sheet.
3.
Has 3 carbons. Each of them has 3 carbons. How many phosphates does pyruvic acid have?
0.
Has 0. So do we have what we started with?
No.
Not
Yeah.
really. We kind of do, right? If you add these two together. Did we split glucose in half?
Yes.
Yeah, by the time we're done, we split glucose in half. All right. So glucose, if you look on the bottom left of your flow chart, glucose has 686 kilocalories per mole. And what that is a measure of energy. That's how much energy it has. How much energy does ATP have? Look on your little chart in the bottom left.
12.
12. Not a lot, right?
Where'd you find
Bottom left-hand corner. Yeah. Okay, so if we use glucose with 686 units of energy in it to do a chemical reaction, that's a lot. Most chemical reactions need far, far less. So we definitely want to break this down into as many ATP as we can get, because you eat the glucose, right? You eat the sugars. We want to break it down so you can do all things like play soccer, play basketball, beat people up, whatever it is that you do, playing MMA or whatever it is, right? Right? And it's okay to laugh at my jokes. Not that your grade's determined by that, but it's okay. Nobody cares that they hear you. So let's look at this. How many ATP molecules did we use up or spend?
2.
We spent 2. So there's a table on that very first page that you need to fill in. We spent 2. Energy spent. We spent 2. And here's where we did it. Why did we spend 2? Why are we adding energy in when we want to get this molecule?
To break down the glucose.
Right? We want to get it to where it's an easier way to break down the glucose.
Yeah.
Okay? So this molecule right here has the highest amount of energy overall than any of the other molecules because it got energy added to it. We okay?
Yeah.
Everything okay? All righty. So we spent 2. Do you know what gross gain means? Do you know what net gain means? You guys probably don't have jobs yet where you get paid from like a business. So if I tell you I'm going to give you $10 for every hour you work 1 hour, how much money do I owe you? I don't.
Wait, can you repeat that? Sorry.
If I tell you, say you're going to do a job for me and I'm going to say, I'm going to give you $10 for every hour you work, and you work 1 hour, how much money do I owe you? How much money are you going to get in your paycheck? Are you going to get $10?
Don't you determine how much we get?
So I said, I'm going to pay you $10 for every hour you work. You work 1 hour. How much should I give you for your paycheck?
$10.
I should give you 10, but that's not what you get. Do you know why you only get maybe $8?
Taxes?
Taxes. I have to send a certain amount of the money that you earned to the government for taxes. Does that make sense? You grossed, you got the total amount, that would have been your $10. But because I had to give some to the government, I had to give some for taxes, you only got 8. The $8 amount is your net. Okay? Now let's apply that idea here. So I spent 2. How many did I gain total? How many should I get total ATP? Total gain.
2. Or 0.
4. See, I was going to get 4 total, but I can't give you 4 total, right? I can't give you $10 total because somebody has to go for taxes. We spent 2, but we gained 4. So how much did we net?
2.
We net 2. Do you understand the difference between gross and net now?
Yeah.
So we gained 4 and we net 2. So out of 686 kilocalories, we had to spend some energy to make some energy. You may have heard you got to spend money to make money. This is the same idea. You got to spend some energy to make some energy. This is not very much energy. All right? Now I want you to calculate what the efficiency is, and I have some calculators sitting there if you need them. Calculate the efficiency of glycolysis. So it says the number of ATP produced, use the gross number, energy required, I already gave you that, it's on the sheet, divided by the complete oxidation of glucose, which is 686, it's on the sheet. I want you to take a minute and I want you to figure out what the gross, what the efficiency is. Okay, if you need a calculator, I have calculators here. I apologize, this is going to be a little bit of a long one today. Erase that to make it easier to see the next part. And again, use the gross number, the total number of ATP produced, not the net.
It's like 0.03.
0.03. I think you're off a little bit. Let's look at the numbers though. What's the number of ATP produced?
2.
No, use the gross number.
Oh.
That's probably where you got off.
4.
So 4. And then how much energy is required for 1 ATP?
12.
12. That's bad. And then how much energy is glucose have?
6.
Remember, oxidation basically deals with the removal of electrons. So if we completely broke down glucose, it would be 686. So do that math and tell me what you get.
Are we rounding now?
We are. I would multiply by 100 to get it as a percentage and then round it up to the nearest ones.
So 0.06 then?
So yeah, 0.069, right?
Yeah.
And then we want it as a percentage, so let's multiply by 100, so that gives us 6.9, let's call it 7%. Do you think that's efficient? 7% efficiency. Yeah, not very efficient at all. Not very efficient at all. Does everybody see how we got this?
So in the box we write 0.069 or
I would just put 7%. Just do it as a percentage. Because doesn't that make more sense to you when you see 7 versus 0.069? Not very efficient. We okay?
Yeah.
Everybody good with this? All right, it's break time.